Okay, I think we are ready to kick off. Good morning, everyone, and welcome to our webinar, Transforming Industrial Waste Gases to Chemicals. This is a joint event delivered by the Bioeconomy Cluster Builder, BCB, which is an ERDF-funded project, and Innovate UK KTN Circular Economy Innovation Network. A short introduction to the people who organized today's events. I'm Dana, I'm from Innovate UK KTN, but representing the Bioeconomy Cluster Builder. Then I joined by Kim from the Industrial Biotechnology Innovation Center, who are leading on BCB. And last but not least, my colleague Michael from Innovate UK KTN, who is representing the Circular Economy Innovation Network. As you can see, we have a really great agenda lined up for you. So Michael and myself are doing the introduction. I will give you a short introduction to the Bioeconomy Cluster Builder, then handing over to Elle to give us an introduction to the Circular Economy Innovation Network. Michael is then going to talk about the action plans he has developed to progress the sector. And then we have some really great case studies lined up for you. So you are going to hear from innovators in the space who will showcase their activities and innovation. Then my colleague Catherine is talking about funding and collaboration opportunities. We then have a panel discussion with all our speakers. So if you have any questions, please save them to the end. And then we are aiming to wrap up around 12:15 with next steps. So Kim is going to give outlines of the next steps for BCB, and Mike is doing the same for the Circular Economy Innovation Network. I'm sure you all have been to our webinars before, but just as a reminder about the housekeeping rules, you are muted throughout the webinar. As I just mentioned, we are having a panel and Q&A session at the end of the meeting, and you can submit your questions through the Q&A function. Should there be any technical problems, please use the chat box, and we're trying to sort them out in the background. As a reminder, the webinar is being recorded and will be published online, and we're also going to share the slide decks after the webinar with you. And to facilitate collaboration and networking, we have Meeting Mojo lined up for you in case you haven't used it before. Meeting Mojo is a virtual event platform where you can schedule one-to-one meetings and have 50 minutes video calls. Please register your profile. Information on how to do that, and the link was sent with you in the email which contained the joining instruction for today's meeting. And Meeting Mojo will be open from 1:30 until 4:30 today. Okay, because this is a joint event from different communities, so we have the industrial biotech community, we have the circular economy community, and the chemistry community. So I would like to brief shortly to introduce the Bioeconomy Cluster Builder. BCB is a 3-year ERDF-funded project. It's a joint collaboration between the Industrial Biotechnology Innovation Center, who are leading on BCB, Innovate UK, KTN, and Scottish Enterprise. And the contact details are on the slide deck. The aim of BCB is basically to increase the uptake of industrial biotechnology and raise the awareness of IB and showcase its application. So it's all about connecting people, bringing communities together who normally not meet. So like the chemistry community together today, together with the industrial biotechnology community. And it's all about improving existing value chains and also developing new value chains. And we really want to encourage the utilization of bioresources, especially in Scotland. So over the last 3 years, we have run over 20 targeted workshops, covering all economic important sectors. So for example, we have done events around textiles, around construction, or also alternative proteins. We delivered awareness-raising activities, so have done showcases. We provided innovation support. So for example, connected innovators with investors so they can pitch their ideas and secure some funding. And also signposting to some funding opportunities. If you remember from the agenda, Catherine will give an overview about funding opportunities and collaboration opportunities later. We have a designated web page for Bioeconomy Cluster Builder, so please get in touch, reach out to us, and a summary of the past events and upcoming events can be found on the web page. And I think that's all I would like to talk about BCB at the moment. Just get in touch, please. And with that, I'm going to hand over to Michael.
Hi, good morning. And yeah, thank you again for joining and the opportunity to be able to talk about the work we've been doing as part of the Circular Economy Innovation Network and transforming industrial waste gases to chemicals. Just next slide, please, Dana. So yeah, just touching on who we are as Innovate UK KTN, just in case people are unfamiliar with us. We're an organisation that is an established, an ever-growing network of challenge owners, innovators, research organisations, solution providers, and coupled that with our workforce who have got a great deep understanding of the industries and the sectors they work in, we're able to bring the different partners together to actually collaborate on projects that really help accelerate innovation and impact the sort of the world and the environment we live in. So if you're not familiar with us, I know that's been really brief, but please get in touch with us if and myself or my colleagues are always willing to help bring organisations together. So with that, if we could just go, next slide would be we'd like to introduce Al Runton, who is actually in charge of the programme for the overall Circular Economy Innovation Network that we've got as part of Innovate UK, and I'll let Al to give an overview of the programme. So over to yourself, Al.
Thanks, Michael. Good morning. I'll just move forward to get the slides on screen. Bear with me just a second, please. Wonderful. Good morning, everyone. Thank you so much. My name, as Michael said, is Elle Runton. I'm a knowledge transfer manager from the Net Zero team. I don't know if any of you have seen this quote from Gartner, but I thought it was worth sharing today because Gartner are predicting that by 2029, supply chains will not be allowed to produce waste. And it's realistic to expect by the 2030s that circular economy will be the only economy. And I think that sets the context for where we are today. Coming together. Michael's already talked about what we do and how we do it. I'm not going into that, but please do look for us online and find out more details. So from a net zero perspective, our focus is in these primary areas. We do lots of work, but just to look at in particular decarbonisation, which for us is very much about reducing emissions and the use of fossil fuels across energy, heat, transport, agriculture, among others. From a place perspective, that's about connecting innovation opportunities at a local and regional level, and arguably into a national level where relevant. And it's important around enabling action by connecting technologies and innovation into established industries. So that convening, connecting role there. And when we look at it from a circular economy perspective, that's about the switch from the linear take, make, waste model that we have into more around a reuse, repair, refurbish, remanufacture, but through those processes, eliminating waste and reducing the demands for fossil fuel carbons. So the Circular Economy Innovation Network aims to enable strong, collaborative industries working together towards that circular innovation. And research shows that if we have specialist collaborations, we're more likely to produce results that wouldn't be possible when people work and think in isolation. So by convening sector communities, we're focused on opportunities for circular design, circular recovery, and circular business models. And we aim to inspire industry to work together in co-creating those pathways that will accelerate the transition for a lower carbon future. And we'll do that through an action plan, and Michael will take you through that later. The three challenges that we have in the network at the moment are around British wool fleece, which is a byproduct of the meat industry, and it's a waste that's often incinerated or burnt. Aluminium, described as the poster child for metals, but valued for its durability, lightweighting properties, and infinite recyclability. And then thirdly, carbon capture utilisation, and today transforming waste gases into chemicals. And through these 3 programs, we're consulting through the value chain, bringing together industry, academia, research organisations and government for positive change. And my pitch is, if you haven't already signed up to get involved, please do find us online and register your details. So why are we doing this? Why does it matter? And I think the key message here is that if we keep doing what we're doing, then the human race will need 3 planets by 2050. And everyone here today, I'm sure, is clear that we have to start addressing carbon emissions, and it's really important in mitigating the impact of climate and warming temperatures. However, there's some other opportunities too, and what's presenting itself is the opportunity to work at faster pace to identify regenerative solutions to reversing biodiversity loss and rebalancing our current negative impact on the Earth's systems. And so outlined the 9 planetary boundaries on Earth. The green circle at the centre, of course, shows us where it's our safe operating space, and the orange fans highlight where we have already transgressed those boundaries. What's interesting and alarming in equal measure, in April 2022, a reassessment of the planetary boundaries for freshwater indicated that that boundary has also now been transgressed. And the results show that due to the inclusion of green water, which is the water available to plants, the evidence is gathering widespread changes around soil moisture, green water-driven destabilisation of ecological, atmospheric and biogeochemical processes relative to pre-industrial conditions. You are probably all more expert in this area than I am, but I think it would be fair to say that global scientists agree that this presents us with a further set of environmental challenges. And one of the solutions that's available is around adopting a circular economy framework, which is a way to help us reduce that environmental impact of our industrial processes, which could lead to more positive climate outcomes. So how do we value this? How do we, I remember that old measure of what gets measured gets managed. And I think when you look at the estimates here, the value of nature to global GDP is estimated to be around about $125 trillion. Interestingly, we've wiped $20 trillion off that number. And the global natural ecosystem, the global value of nature and natural ecosystem services is directly linked, it would appear from this chart on the right hand side, to where we are with our produced capital. And we can see that we have increased human capital, our skills and knowledge has increased. But this exponential rise on the right hand side in produced capital from economic growth linked to manufacturing and production of the things that we use and buy every day appears to be coming at the cost of the Earth's natural capital. And you can see a 40% per capita reduction there. This has been tracked by UK government, and data from 2020 showing the UK value of $1.8 trillion per annum through natural capital assets and services. So I guess the big question today is, how do we preserve this? One of the globally accepted solutions is around the adoption of the circular economy as a framework in order to be able to reverse biodiversity loss and create climate positive outcomes. And this chart on the right-hand side here is the result of Ellen MacArthur Foundation and McKinsey work. And it's showing the separation between technical materials, represented in blue on the right, which cannot re-enter the environment without human intervention. And that would include things such as metals, plastics, and synthetic chemicals. And therefore, they should be continuously cycling through that technical system so that their value can be captured and recaptured. Conversely, on the left-hand side in green, you're looking at the biological materials, which are usually regenerative in nature. That would be things like cotton, wood, mycelium, wool, etc. And so when we have products using natural materials, or and that might be something like clothing or wood furniture, that can be circulated through both the technical and biological cycles. But ideally, the material types would be separated so that they can safely be returned to the biological cycle from which they originated. So the core principles for a circular economy framework are based on design, and that's about eliminating waste and pollution from the outset. And this design is very much about taking into account how a product or service is made, its material parts, but planning the end of life before that life cycle even starts. It's about setting the intention to design for recovery and understanding revenue growth within the planetary boundaries. And from the outset, considering the end-of-life solutions that are available now and factoring those into the go-to-market strategy before launch. Circular design specification, or taking into account the overall environmental impact over the course of the full lifetime of the product or the service. So of course that gives the opportunity for designing items for extended use, which then means that embedded emissions are spread out over the long time that the product is in use or in circulation. The second area then is around circular recovery, and that's very much about redefining systems to retain every asset possible across the value chain and procurement processes. And it's a way of reducing the amount of new feedstocks needed and starting to mitigate against cost increases, but also moving us towards greater resource efficiency. And the challenge for many businesses is that Scope 1 and 2 emissions are more likely to contribute to your customers' Scope 3. And as Scope 3 often accounts for more than 70% of the business's carbon footprint, it's a significant challenge for many. So whilst the reporting of these emissions is not currently mandatory, it's a strongly recommended line under the streamlined ECR UK regulations for emissions and carbon, which is, you've probably seen, has been recently published. We have the opportunity with CCU where waste becomes an asset or a feedstock, and it's not a liability that you pay to dispose of. So carbon capture, recovery for utilisation is one of the strategies to deploy waste as a resource in another part of the value chain and as a potential on that pathway to reducing the consumption of fossil-based virgin materials. And then the last pillar is around business models, and that's very much about slowing down slowing down the flow rate. And business models helps us to create and deliver value to a wide range of stakeholders at the same time as eliminating waste and environmental damage while those products and materials move around the economy. So slowing down that material flow offers commercial opportunities to generate incremental revenue or reduce expenditure, at the same time as transforming relationships with customers, building loyalty, or indeed starting to put some mitigation strategies around supply chain, particularly if that material is onshore in the domestic flow. To be effective, products have to be designed to enable business models such as disassembly or repair or remanufacturing, refurbishing or remodeling. And that's not a new concept. You know, our great-grandparents did it. But somehow businesses have moved away from that into that linear take, make, dispose model. Using a circular economy framework offers a way to reposition that appeal and reduce that embedded carbon throughout extending the life of materials and products. Some of you may be familiar with Fairphone, who reignited that do-it-yourself at-home mobile phone repair. And last weekend, Nokia had launched a low-priced smartphone, which is designed to allow battery replacement at home within 5 minutes. Although it might take me a bit longer because I'm not very technically enabled. But if I move on to my final slide here. Apologies, technical. My final slide here is really about saying the Circular Economy Innovation Network here is about linking together challenges with solution providers, being able to do that through Innovate UK at a local level and also through our global network, providing access to knowledge transfer partnerships, connecting academia and business challenges, insights and reports in the action plan that you'll see today, but also access to funding, investors and collaborators. And the circular economy offers a compelling framework for systems change. It's a transformation from business as usual, but it does come with challenges. For large and small organisations, a circular economy innovation network is here to support, navigate that path, collaborate across value chains, and learn together how we can catalyse innovation that will accelerate the UK's lower carbon future. Thank you, Michael.
Thanks, Elle. I'll just share my screen. Thank you for providing the information on the central aims and objectives of the circular economy and the network. What I'd like to do now is take you through an overview of the actual the Transforming Industrial Waste Gases to Chemicals Challenge as part of that network and the action plan that we've been developing with the community over the last year. And I just want to say a big thank you to all those who've already provided us with a lot of support and input so far. We really look forward to continuing to expand our network and just working with all of you to take this action plan forward. Now, the action plan will be available for download in the next couple of weeks on our website, and we'll send out a link when it's available to everybody that's on the webinar today. So why did we actually pick this challenge? What's the opportunity we have? Well, to start, maybe looking at the answer to that question, maybe start looking at how much carbon is being used and emitted in the chemical manufacturing. Now, from the work of the Renewable Carbon Initiative and the Nova Institute, they've got some reports, and one of those is that the carbon footprint of most chemicals and the chemical intermediates we manufacture is that a third of it is actually from the manufacturing process, but actually 2/3 is in that embedded carbon that exists within the chemicals. Now, another report they have is that global demand for that carbon that's embedded in those organic chemicals is in 2020 was around about 450 million tons per year, with 85% of that being fossil based. Now, their actual prediction is that that's going to continue increasing by some significant margin by the time we get to 2050. Now, this really, for me, just highlights why we have a challenge and why the amount of carbon is needed. It makes a compelling case that we need to be using alternative feedstocks and all the alternative feedstocks that we have available to us for carbon if we want to move away from that fossil-based source of material. Now, the references for those reports are cited at the bottom of the slides, which will be made available afterwards. So what's the opportunity for the UK? Well, the Climate Change Committee's 6th carbon report in 2020 showed that the UK emitted over 480 million tonnes of CO2 equivalent, where actually 66 million tonnes of that was actually from the manufacturing and construction industries. And the chemical sector itself was even responsible for over 9 million tonnes of that. So I think by focusing on industrial waste gases, there's an opportunity to utilise those those emissions, which are often more from a point source, because a lot of the other sources that are on that chart are actually from transport. So having point sources of emissions that we can use has an opportunity to really have a significant impact on reducing our carbon emissions. But is the chemical industry worth it in the UK? Well, actually, from the Office of National Statistics, even in 2020, the industry was still reported to produce £32 billion worth of turnover and £11 billion worth of GVA. So I think based on the size and its direct contribution to emissions, the UK chemical sector definitely has a role to play going forward. So as we drive towards a more sustainable chemicals and we want to replace that fossil-based carbon, our challenge is how do we meet that demand with carbon using these alternative sources and developing these circular carbon approaches. Now, carbon capture utilization of industrial waste gases really does allow us an opportunity to lower our carbon footprint for chemicals and move away from that fossil, that sort of virgin fossil source of feedstocks. And it really gives us an opportunity to reduce our scope 1 and 2 emissions from within the sector. But it really also has a good chance, because of that embedded carbon, to lower the scope 3 emissions as well in the products and materials that we're making. So as part of the Circular Economy Innovation Network, we've brought together this community to develop this action plan, and we're going to go into that in more detail now. And we'll provide an overview of. And what we now need to do is continue expanding our network and actually deliver on the action plan. And as part of this network as well, we're really keen again to do what we can do best in forging those collaborations, to look for challenges and leveraging these collaborations to accelerate innovation. And I'll mention later a particular program that we've got, which we think can actually help us on that, which is Collaboration Exchange. So for our action plan, we've kept the vision and the aims quite simple. If we want to protect our environment and meet the demands of an increasing and aging workforce, then our vision is that we need to capture the industrial waste gases and we need to utilize them to make chemicals and actually move towards this circular carbon future. Our aim is really just to be able to create this circular, sustainable and net zero chemical sector and its associated supply chains that can thrive in the future, building UK competitiveness and resilience. So what do we want to have as outputs from this action plan? What do we think we could try to achieve? Well, one of the things that we got from the community is that we need to be producing a clear and consistent message. And this message needs to be able to show why the UK chemical sector supply chain has this important role for achieving net zero. We need to be able to look at how we can justify that the UK is the right place to manufacture chemicals and actually build the supply chains from alternative feedstocks. And then within that, we need to be clear on what the key opportunities are for the technologies that exist and those that are emerging, and how we can use those to in the UK to really build an opportunity for the future. Underneath that, we know we want to produce some roadmaps and timelines for the various technologies and supply chains to give a clear indication of what we can achieve. In association with this as well, we know that we need to have an environment where the policy and regulation and the standards really sort of promote the adoption of this type of technology and actually accelerate us from where we are now to where we really need to be. And in accompanying that, what we really want to do as well is encourage investment into this area as well, certainly in the creation of things like pilot and demonstration facilities. And to really sort of make the point and help, we believe that, we need to get some flagship projects. We need to look at what we've already achieved, and we need to be promoting that to really show to business leaders, to government, what can be done in this space and what we can achieve in the future. Now, Elle went through those different pillars, and I want to go through what some of the key actions that have been raised. There's more detail in the actual action plan itself. Some of it will be in the slides that when we send them out, but again, please go to the action plan when it's available, download it and have a read through it. So the first pillar is around this designing for circularity. So when we work with the community, for us, this was about what we make and how we're going to make it. And I think that what came from the community as well is that we're not aware of all the things that are done within the UK. We don't what data is available. And actually what we need is mass and energy balances around the requirements for the electrons, the carbons, the hydrogen, the water, the waste emissions that we have, the availability of that now and in the future. What we actually manufacture, what's our current supply chain, what do we manufacture for chemicals in the UK, how much we're using, what do we need to make now and what do we need to make in the future, and getting that information to build some concrete plans upon is something we need. So some specific things there. It's fair to say there is some existing information. We do have relevant data available. We just need to make that so it's identifiable by the community. But for where we already know we still have some gaps for both industrial clusters and dispersed sites, then we need to do some more in-depth research and studies, evaluating maybe the near long-term opportunities and the availability of those resources, especially when we consider other demands like sustainable aviation fuels, the impact of fuel switching and electrification, and how that may change this landscape as we go forward. We need to be able to produce this sort of clear picture of what it is we think we can achieve built on this data. And the data is really something, a foundation we need to start from to be able to identify maybe where the demand is for sustainable chemicals. So the next pillar then in the action plan is around the business models. So how are we actually going to achieve the environmental success? And also how we're going to generate the revenue. Now, building on the data, we need these circular business models, and we need these business models that are actually developed across the supply chain, incorporating sort of from the emission all the way to the end use, and even then looking at how that is going to be reused or recaptured. We need to use the data to use a techno-economic analysis and life cycle analysis, again, across those supply chains to make sure we get the assurances around these new chemical pathways and the sustainability of doing what we're doing. Now, to achieve some of the specific actions that we've got within the action plan is even to be able to standardize what we're doing around life cycle assessment and techno-economic analysis. Making sure we can talk a common language across the supply chain and even within the same sector. When we're all doing these different options and look at valuations, we need to be able to know that we can compare what we're doing. We need this data to really start helping build this justification, again, why we can do this in the UK, why we want to manufacture, and that what are the right routes for doing that. It's easier said than done, a real big challenge in this, but I think there's some great opportunities to then build these models and actually then identify some of the key opportunities we have now and in the future, leveraging existing infrastructure, but also looking at how we can plan for the future. So The next pillar then is around circular recovery. So this is about how we recover value from materials and products, and we've broken this down into 2 stages. So the first one is around the carbon capture itself. So what we know is that we know there's capability already, there's commercially available for carbon capture. And we also then know there's some other emerging technology coming through the pipeline. In both of those cases, what we found as a community as a whole, it's not necessarily clear to the community what is the capability that already exists and what's coming through the pipeline, but what is this, how scalable is that? What's the right selection of that technology for the right feedstock or the alternative feedstock that we've got, the waste gases? And what's the right technology to achieve the end, the purity of what we need to achieve for the chemical transformation? And so it's building information and confidence in what's already available and what we need to have in the future. And so we need to build that knowledge. But equally, with the capability we've got, we still need research and development and deployment of that emerging existing technology for achieving at-scale capture within the UK and making sure we can achieve that business case that we need that would have been developed within the models. So to support this, there's desktop studies need to be done around what is the current state of the art and emerging technologies, making that available then for the community. We also then need to be generating data that can actually go into the things like the techno-economic analysis and the life cycle analysis. I mean, to do that, we may need more investment, but I think that what we need is investment in pilot and demonstration facilities for that de-risking scale up, but also in those novel carbon capture technologies that are still coming through to really reinforce the business models. The next section is then focusing on increasing innovation and investment in the chemical manufacturing. So this is about the chemical transformation itself and how we take this carbon dioxide or carbon monoxide and how we convert that into a useful chemical. And similarly, it's similar to the previous action. I mean, we need more investment in technologies and projects that just embed that carbon, and we need to be doing it, looking at what the opportunities are that suit the UK. Certainly, we're aware as a community that there's commercially available processes that can do this already. But there's also space for more research and development in the new technologies that are coming through, whether that's chemical or electro or bio, to really sort of help understand what what we need to do to achieve the sort of environmental success as well as the economic and social requirements that are needed. So it's not surprising. Similarly, there's opportunities that what we want is desktop studies that collates all the available data again of the state of the art emerging technologies. But again, we want to drive more investment in this by driving more investment in this area, we can establish the capability and the scalability of the different technology for those business models that will work for the UK. And, you know, there's more deployment, again, of that pilot and transform and demonstration of facilities to de-risk scale up, as well as the sort of novel technology that's coming through. And again, there's a big need to continue doing ongoing community activities to keep us working towards driving innovation and deployment. So the final pillar that we came up with in the action plan was actually around the government framework for circularity. You know, we mentioned before that we need to really have an environment that drives the behavioral change and drives deployment of this technology for the UK and making it an attractive long-term investment. So what we want to be able to do is work together on the policy and the regulatory mechanisms that will help achieve that. But then there's also things on standards around the life cycle analysis, the techno-economic analysis, and the sort of the carbon itself. So what's clear, there's lots of discussions, and there is actually some key individuals that are doing a heck of a lot of work in the space of current policy and regulation and what needs to change. But we're all aware of it. I think what we need to do is produce a summary of what the current policy is, the regulation that exists, and what the gaps are and what the needs are to be able to all work towards building a case for what the policy and regulation changes need to be. And as we're doing this work with, we're going to be using carbon from emissions. There's a question about how we measure that, how we keep that, how we trace that, and how we then handle the chemical products and what standards need to be in place to make sure that we can do that, and the system actually works for what we're trying to achieve. Then I think within this space, we know very quickly we reach a point where we get to the projects being very capital intensive. So again, all the work that we've sort of talked about doing preceding this should really help build a strategic case to government for further investment and support in this area. And then something the community came up with as well is that we need maybe an option for a virtual circular economy policy centre, because often we need to give evidence really, really quickly to government about what we need to do. And actually, there's a lot of information out there. So there's an option there that we have identified centre consisting of some key experts that are aware of the state of the art, the emerging technology, the current policy that we can leverage to actually give a unified response and make sure that we give a clear message to government about what the opportunity is and what we need to do in this space. So that has been a real quick overview of the detail in the action plans. Please, I know that's been a bit of a dry topic going through, but I think it's really important, and I hope you'll join us as we keep building and growing our network. What we're wanting to really do, we're going to continue championing this. We're going to help try to drive the actions forward. We're going to act on the actions KTNs can specifically do ourselves. We've already started, and we continue to need to identify support and leadership for all the other actions. So really, if this is something that you feel you can contribute to, you're interested in, or if there's a particular action area you think you want to be involved in, then please reach out to us, join the network. The link is on the slide. You can reach out to us through that or connect to us via our email addresses. Please want to hear from you. We're really keen to take this forward. What we're also keen to do, as I mentioned before, is actually help forge collaboration between different partners. And we'll hear from Catherine later on about some upcoming funding. Again, if that's something we can help you with, then please reach out. I've mentioned Collaboration Exchange before. Now, this is just a new platform that we're building. And the idea of that is to amplify what we do as a KTN and connecting people by providing an actual platform where we can advertise a challenge and help solution providers or partners submit applications to that challenge to actually form this multi-partner collaborations. It's a really unique way of reaching out to people across the UK, leveraging the power and the strength of KTN's network. If that or any of the other ways where KTN can help you is of interest for any particular challenge you have, then we really want you to reach out to us. I think that's all I have to say at the moment. So with that, I'd like to now hand over to Sean from Croda, who will talk to us about Flue2Chem, which is a great example of a flagship project operating across the supply chain and looking for optimal pathways and developing a business case in this exact space that we're talking about. So with that, I'd like to hand over to yourself, Sean.
Thank you, Michael. Hopefully you can see those slides okay.
Yes, we can.
Okay, brilliant. Thanks very much. So, good morning, everyone. As Michael said, thank you for the introduction. I'm Sean Rouse, technology specialist with Croda, a chemist by training. And it's my pleasure this morning to have this opportunity to tell you about this exciting project, Flue2Chem, which is, as it says on the title there, it's about redesigning and validating a UK value chain to convert industrial, waste gases or gaseous resources might be better, fossil, non-fossil, into sustainable materials for consumer products. I should stress that the emphasis is very much on the whole value chain. Here's the agenda for my talk. I'm going to go through why Flutichem is needed. I'm then going to move on to what Flutichem will do, why we've chosen what the molecules we've chosen, the team and their roles, a little bit about the money. I'll then move on to carbon flows and how we can change them. And then I'll finish up with a slide on next steps. So firstly, why do we need Flutichem? Well, this is, I guess, the crux of the matter. And this graphic illustrates the scale of the problem. We take all this virgin fossil carbon from the ground. On the left-hand side, there's a lot goes into fuel, which is then burnt, releasing CO2. But then there's also a significant amount used to make chemicals, petrochemicals, which then degrade and release more CO2. So there's all this CO2 being released, and we know what that's causing. To put it bluntly, we're not going to reach net zero unless we find other sources of carbon. Moving across, the science is well known at lab scale. You know what we can do with CO2. It's not groundbreaking, but the big question is, can it be made to work at scale and at the right cost? And that's really why we're looking at the whole value chain. At the moment, we're focusing on the consumer market because that's got the biggest immediate driver for change. You know, consumers want to switch, but government and manufacturers need to act to help them. And I think that's a key point. Flutichem will hopefully help blaze a trail as well, so that it facilitates similar supply chains, so that other carbon uses can also move away from fossil carbon in a timely manner. So things like plastics, paints, adhesives, insulation, etc. There are all these other areas that hopefully this will guide in the future. There's a big UK transformation agenda aimed at clean growth, and the amount of funding reflects the scale of the challenges we face. On the left, we've got details of the Industrial Strategy Challenge Fund. So there's a lot of public money matched, slightly more by the private sector. And then there on the right, there's details of the Transforming Foundation Industries Challenge. Now that's part of the Industrial Strategy Challenge Fund, and in that is where Flutichem sits. So that's where the fundings come there. I guess I'd just like to dwell a bit on this slide, and I don't know if people saw the report that Tony Blair and William Hague released the other week about how innovation can power the future of Britain. And in that, one of the things they spoke about was the speed of the COVID response and the development and deployment of new vaccines, and how that showed what can happen when the government and the private sector mobilise effectively behind a clear purpose. And that's the kind of thing that we're doing here with Flutichem, and it's very important that we do act in harmony and unison. Moving on to what Flutichem will actually do. Who's involved? What will we deliver? So the overarching aim is to make ethoxylated surfactants for consumer products from UK emissions. So why ethoxylated surfactants? You can see some numbers at the bottom. They're large, both in volume and total value. They go into a wide range of consumer applications. But quite frankly, they're not particularly green when it comes to emissions. You know, if they're made from fossil carbon, then yes, there's that release of greenhouse gas at end of life. If they're from palm kernel oil, yes, they use biogenic carbon, but there are issues with deforestation, and there's still greenhouse gases released at end of life as well, which come from the value chain. And an important thing to note, given that this funding is about UK PLC, is that they're generally imported to the UK as well. So the entire value chain is in scope. It's about taking second use emissions, so black carbon from steel and biogenic from paper, capturing and purifying them, converting these gases to fatty alcohols via hydrocarbons, and then also converting the gases to EO to give those raw materials for the surfactants. As I mentioned earlier, it's not groundbreaking, but can we do it in a joined up way at credible economic scale? Essentially, we're talking about a new business model. You can see the logos of the partners in the consortium. You know, they represent the whole value chain, with the lead partner Unilever. Here's a photo of the team members who took part in the face-to-face kick-off meeting last October, where they did team building, they created a shared vision, they developed the project plan, put all the network for the activities together, and then put together a collaboration agreement. And that in itself is a huge achievement in getting this project off the ground, especially that collaboration agreement. You know, it's an example to the rest of the world, let alone the UK. Tremendous effort on the part of the project manager, Al Sanderson from Unilever, front row centre. He's in the audience today, so I hope I'm doing a good job. He's put together a biography of all the team members, totaling up the experience we have, and it comes to more than 700 years. You know, and that experience will be needed, I'm sure, as we progress through these 2 years of the project. As I said before, the overarching purpose is to take those gaseous, I'll call them side streams from industry, and convert them to create more sustainable consumer products, with the long-term goal of helping the UK cut emissions, you know, potentially millions of tons of carbon dioxide, so that we can reach the net zero target. What's really amazing, though, I have to keep coming back to this, is the cross-sector collaboration involved in this 2-year project. The who, so we've got the names of all the parties shown on the right, all the way from the foundation industries up to the FMCG manufacturers, with 2.68 million funding from Innovate UK, matched by the commercial parties to give a total project value of over 5 million. A more in-depth look at the who and the what on this slide. So on the left, we're starting of the value chain with gaseous side streams from the foundation industries, so steel and paper, so at Tata, UPM and Holman. And those gases are then captured using 2 different technologies, by Carbon Clean and by Sheffield University. Moving right again, the gases are then converted into our component raw materials, fatty alcohol and ethylene oxide, by the teams at BASF, Johnson Matthey, the Centre for Process Innovation up at Wilton, and again Sheffield University. But what's really important here is that when it comes to the fatty alcohol, we'll be looking at both biotech and thermocatalytic routes. So we're not saying that one way is better than the other. Now, generally, the biotech people say our route's best, and the chemists say, no, our route's best. Well, we're not saying that one way is better than the other. We're going to do the science to work out which is best for this particular problem. We know that short chain alcohols can be done, but how do we get to C12, C14 that we need for these surfactants using real emissions? Moving along to 3B is where Croda and I come in. I have to say that I'm thrilled to be involved in this project, which I feel it's really going to make a difference and provide humankind with one of what I'm sure will be many required solutions to the climate crisis. I'll be overseeing making the ethoxylated surfactant, which will then be passed to the next stage where Unilever, Reckitt and Procter & Gamble will assess its performance in cleaning products, and Tata Steel again will evaluating it in coating, so quite circular there. And then the Confederation of Paper Industries is looking for wider application in its sector. We've got the SCI doing a great job of dissemination of progress and outcomes from the project. And then overall, we've got Surrey leading the techno-economic evaluation and life cycle analysis that will demonstrate the benefit of this new value chain. I'm not going to dwell too much on this slide, but really it's about Scope 3 emissions, they're hard to pin down, how to reduce them. I'll talk about them again in a later slide. So this brings me on to the carbon flows and how can we change them? What's the project going to do with regard to that? So again, we've got another fantastic graphic that shows how reusing the gaseous side streams can lead to reductions. On the left, we can see what happens currently. We've got virgin fossil carbon which is used in steel production, and then that's released to atmosphere. And then we've got organic chemicals, again using virgin fossil carbon, degrading, releasing to atmosphere. If you move to the right, with Flutichem, the scenario changes to that shown. So we've got virgin fossil carbon used to make the steel, but then capture of those point source emissions and using them to make chemicals removes the need to take further virgin fossil carbon out of the ground to provide the potential emissions reduction as shown. The picture is even better for industries that use biogenic carbon, for example, paper production. So on the left, we've got trees as our source of carbon going into the paper mill, which are then released as CO2, which is recycled back into the trees. But the chemicals on the right of that half of the slide, they're still using virgin fossil carbon, degrading, releasing that carbon to atmosphere. If we move to Flutichem on the right, we reuse those point source emissions from the paper mill to make our organic chemicals. That CO2 is released, but now instead, so the arrows shows it going back to the paper mill. It really should extend to the trees. So we've got a circular loop where all the carbon is biogenic and recycled biogenically, creating the circularity we need, a virtuous circle, in fact. But it's not just about where the carbon comes from. So we've got where the carbon comes from. We've got the carbon rainbow. We've got black, grey, blue, green. I'm trying to remember all the colours. And purple, which is the captured CO2 one in the Unilever carbon rainbow. But we've also got the value chain emissions. So these Scope 3 emissions, which, as I said, they can be really hard to pin down and reduce. It's well illustrated by the infographic from Michael Carris's Nova Institute at the bottom, how you've got the embedded carbon and the production carbon in all these materials. And he's right, we're not going to stop using carbon, but we have to start using the right carbon so that we avoid adding more carbon into the atmosphere. And finally, I'll finish up with a slide on the next steps. So what we're going to do, yes, on the left, we're going to design and build that value chain to convert these gases into sustainable materials. We're going to demonstrate that it's possible to make these surfactants from waste emissions. and thereby show that it's possible to mitigate these waste emissions from the foundation industries. Will also importantly displace the import of non-sustainable materials from outside of the UK, doing the work that will be required to make it work, this business model work. And the bottom line is it's about driving the world by innovating in the UK. It's important, and also important to emphasise that we want it to act as a foundation which can be built on in other industries. And then finally, just some thank yous to all the partners involved in the project, especially Al from Unilever, Maxine Bosma, David Bott and the SCI team for the great slides, to KTN for the invitation today, and thank you all for listening.
Thank you very much, Sean. That's an amazing project.
So my name is Chiang Lee, and I'm here to represent the Centre for Process Innovation. And thank you very much for Sean's wonderful introduction to Flow2Chem. And I can also say that I feel really honoured to be able to present the biotechnology part of Flow2Chem project on behalf of CPI. So I don't know if you have noticed that actually two CPI in a consortium. So we're the Centre for Process Innovation. We are the research technology organization operating in Wilton. And one of the business at CPI is the industrial biotech. So we run open access facilities in this area, and we help the academics and SME to develop, prototype, and commercialize their product and process. The other CPI, I feel obliged to mention them as well, stands for the Confederation of Paper Industry. I think it's worth making this distinction between these two, is to demonstrate that RTO, like ourselves, one CPI, is developing the technology to help the paper industry to decarbonize their CO2 productions. If I may just give a brief introduction about the biological CO2 assimilation pathways. As we all know that there's CO2 fixation pathways existing across many kingdoms of lives, but their efficiencies vary from organism to organism. For CO2 assimilation, usually it also requires some energy input, and that can come from hydrogen, electrons, or light. And it's worth mentioning here that the synthetic biology is playing an increasingly important role that can help to improve the efficiency of those biological pathways. In today's webinar, there's a number of companies presenting some of the funding industrial biotech and synthetic biology as well. Maybe we come back to about the biological parts of the CO2 assimilation in the Flow2Chem project. As Sean has mentioned, we do have two different routes for CO2 utilization. One is the biological pathway represented by CPI, and we also have a thermocatalyst pathway. I'm not drawing any conclusion which one is better, as Sean put out in the beginning, but I think it's worth mentioning a few differences between these two routes. So for biotech routes, usually it operates at ambient temperature and pressure, so that relatively speaking has a lower environmental impact in comparison to the thermocatalyst pathway. And the other thing that was mentioning is for the thermocatalyst pathway, it usually has very stringent requirement on the CO2 gases to be used as a feedstock. In comparison, the biological pathway usually is quite tolerant towards the other impurities from the flue gases. So that may have some positive impact on overall economic. As we all know, that CO2 is waste gas that we're all trying to get rid of. But however, we're talking about utilizing to make something useful, the price usually go up. That's mainly because of the cost associated with its purification from the flue gas. The downside of the biological pathway, I don't see many people talking about this. Usually the reaction rate is slower. So that is often offset by the very large bioreactors. So scale up is really a challenge in the biological pathway. So as you heard from Sean, the purpose or objectives of Flow2Chem project is to help to decarbonize the surfactant industry, and one of the surfactant chemical entity we're looking at is the is fatty alcohol ethoxylate. And we're looking at how we can utilize the biological pathway, native biological pathway, that is fatty acid, to help to achieve that target. So the fatty acid synthesis is a fundamental part of cell metabolism and is well characterized. The challenge here is that usually it produces aliphatic C16C18 fatty acid, while the fatty acid required by the surfactant industry is C12C14. So there are some genetic tools reported in the literature which can change the titer and also the chain length of the fatty acid produced. But the challenge here again is that these genetic modifications often interfere with the native fatty acid synthesis, which is an important part of the cell life. So what we will do in this, what difference we're going to make in this project is we will study the effect of the targeted genetic mutations on fatty acid synthesis in some of the CO2 utilizing microorganisms, and utilize the unique capability of CPI in gas fermentation, string engineering, and process optimization to help to improve the product titer and also change the carbon chain length of the fatty acid produced. So as mentioned previously, fatty alcohol ethoxylate is the target we're trying to produce in this project. It has wide applications in the industrial. It has wide industrial applications other than the non-ionic surfactants as well. So in this biotechnology routes, in summary, we try to explore the opportunities of medium chain fatty acid production by technology called gas fermentation using genetically modified microorganism. And subsequently, this fatty acid will be converted into fatty alcohol using hydrodeoxygenation that involves a chemical reaction. And this fatty alcohol will be passed over to the project partners to further convert it into the fatty alcohol ethoxylate, which is a key component of the surfactant. So that brings to the end of my presentation. I hope that this really high-level summary of what CPI and what CPI do in the Flow2Chem project will help you, give you some flavor about the Flow2Chem projects as well. As you can see, I left my contact detail in the slides. If you have any questions, feel free to drop me an email or give me a call. And I will also be staying in the Q&A session after my presentation. So happy to discuss with you to see if there's anything that we can help you with your applications. Thank you, Michael.
Thank you. That's great. Thanks very much. I think that was it was a real good insight into what's happening with the project. Just interesting time. If we could just jump straight onto Roxanne, if you're happy to share your screen. Roxanne is going to talk to us about some project they have in Ingenza.
I'm just making sure everyone can see my screen. Can you all see my screen okay?
Yes, yes we can.
Perfect. My name is Roxanne Cortis. I worked at Ingenza for over 10 years and my background is mainly strain engineering. So the talks I take at this talk is more biology based than what's been discussed so far. So what I'll be discussing is the project that I'm involved in at converting industrial waste CO2 into value-added chemicals. So I'll give a brief description of the company itself, outline the outline and the background for the project I'm working on, and the strategy that we're taking to address conversion of waste gases to value-added chemicals. So who are we? Ingenza is a company based in Edinburgh, in Midlothian, in a little town called Roslin. We are a world leader in engineering biology. We mainly specialise in the design, development and biomanufacture of chemicals, biologics, pharmaceuticals and biofuel products. And we've been successfully delivering for our customers since 2003. We have a very multidisciplinary team, which I'll go on to in a second. And we have very flexible collaboration and business models. So our team is quite diverse. So we have a molecular biology team, which I'm part of, and we mainly do the upstream processing. So looking at the most suitable hosts that we'll be using for a process, and then coming up with a design strategy on how to convert this host into a bioreactor to deliver our project. So in this case, it'll be expressing the enzymes necessary for conversion of CO2 to formate, which I'll go on to in a second. And then this then gets fed into fermentation, and we have a lot of expertise in a variety of bacterial, yeast, mammalian cell culture, and the department usually designs cost-effective and scalable bioprocesses, and there's comprehensive tech transfer documentation for that as well. And the chemistry department usually underpin everything that we do, so that we can giving us the analytical method developments required for our assays, doing biocatalyst screens and custom assay developments, and a lot of the downstream processing for product isolation. So moving on to the organisms that we have expertise in. Of course, you've got E. coli, which is our main model organism. We have years and years of experience in using this organism, and the largest synthetic biology toolbox there is available. We also have experience in Bacillus for secretion of heterologous proteins, and also has the advantages. Bacillus has a long history of industrial exploitation. Pseudomonas putida, which is naturally highly tolerant to solvents with a diverse metabolism, and again, a well-defined genetic toolbox. We've got experience with Streptomyces, which has a complex secondary metabolism, and it can produce numerous medical compounds. Corynebacterium glutamicum is very good for heterologous protein and small molecule secretion with high cell-specific productivities. Vibrio nitrogens is a very fast-growing biological host with a doubling time of less than 10 minutes. Saccharomyces cerevisiae, another model organism, which is GMP compliant for pharma and generally regarded as safe, with a large toolbox and is very highly scalable. Pichia pastoris is very good for the secretion of recombinant proteins, and it can be engineered for humanized glycosylation, ideal for pharma. We also have experience in Aspergillus niger, which has the capacity to secrete large amounts of enzymes, and has been shown used for the production of citric acid and various metabolites. And we also have experience with mammalian cell lines such as CHO for human post-translational modifications and targeted gene integration. So the organism that we'll be focusing on is E. coli. So who are our customers? So Ingenza has numerous different projects with a variety of collaborators across the world. We've got a few of them are shown here. So we have projects in pharma, consumer goods, agrochemicals, where we're outsourcing pathway optimization, enzyme evolution, protein expression for biomanufacturing or new product functionalities. We work with chemical companies developing bio-based chemical products for superior to develop monomers and other intermediates. And we have collaborations with academic groups advancing early stage research for proof of concept mainly. So moving on to bio-based conversion of waste gases to formate. So the project is funded by Bayes in collaboration with Johnson Matthey. And the main aims of the project are to look at novel enzymatic carbon capture solution for efficiently converting carbon dioxide to formic acid, formate salt, which is more of a commodity chemical that has many uses of its own, which I'll come on to later. And then building on the previous feasibility studies to determine if this technology can be improved for a cost-effective removal of industrial waste, carbon emission, waste carbon emissions at scale. So the project itself is 24 months. And the first part of it is looking at strain engineering, small scale testing, and then the next phase is in blue, where we've got the process development, large scale feasibility assessment, which will be led by Johnson Matthey, hopefully ending with a pilot test at the end of it. So what I'm going to talk about now is the intracellular enzymatic production of formate from hydrogen CO2. So this work was performed by Frank Sargent's lab at Dundee at the time in collaboration with C1Net and Sasol. So the enzyme that we're looking to exploit is the formate hydrogen lyase, which normally the primary function of it, native function of it in E. coli, is when formate's imported into the cell, the forward reaction converts this to carbon dioxide and hydrogen. But there's also a reverse reaction which occurs, which uses carbon dioxide and hydrogen to produce formate, which is exported out of the cell. So our process mainly relies on the enzymatic conversion via formate hydrogen lyase, which I'll refer to now as FHL, of CO2, which is our waste gas, to formate, which is a useful feedstock. As I mentioned, there are two directions of this process. The native uses formate, and the reverse reaction produces formate, which is non-native. The reverse reaction requirements are anaerobic conditions, so the absence of oxygen, and high levels of hydrogen, CO2, and under higher pressure, which allows better solubility of the gases into solution, driving the reverse reaction for the production of formate. So this is a schematic of the experiments that Frank's lab performed, which is the basis of our project. So if you look at the graph, you can see there are three main things that you're looking for. The first thing is at lower pressures, so 200 millimoles. At 200 millimoles, you have low production of formic acid from hydrogen CO2. You increase this pressure, and the production of formic acid increases further. And then if you increase the pressure and also add sodium hydroxide for extra buffering of formic acid being produced, this improves even more. And then once you have this system and then increase the pressure, you get the highest level of formic acid productivity from hydrogen CO2. So in this experiment, it was demonstrated that you could get 100% conversion of gaseous CO2 to formate, giving over 500 millimoles extracellular formate being measured. This can be used as a carbon capture technology in the form of formic acid, which is a building block feedstock for other higher value chemicals. And as you can see from the schematic of our E. coli cell, here's the expression of the native FHL enzyme. You've got the pressurized substrate CO2 hydrogen being imported into the cell. And then once it's being converted to formic acid or formate, it gets effluxed out of the cell into soluble formic acid. And this is just a schematic of the pressure, lab scale pressure reactors that can be used. So moving on to the proposed continuous process that we have targeted. So we have the overall process, which, as I mentioned, is the conversion of carbon dioxide and CO2 via FHL into a formate salt. So the idea is we have the waste gas emissions, which will be fed into our system, along with our base feed and renewable hydrogen. The fixed bed reactor should contain our FHL biocatalyst, and the output would be formate salt, which can be used in a range of different, has a range of different downstream uses, such as animal feed, a food preserver, de-icer, detergents, material processors, and then the secondary market of fermentation feedstocks, hydrogen carrier, so it's safer to transport than hydrogen, and has lower risk associated with it, and gives you a transportable form of a carbon capture and storage system. So then the work that we'll be doing on the project, such as using the E. coli as a workhorse for the carbon capture and utilisation. E. coli produces this enzyme, FHL, as a native function of itself. So it doesn't need to be engineered into the host. So this removes that complication. This reaction was evolved as a mechanism to detoxify high intracellular concentrations of formate, because high levels of formate can also be toxic to the cell, hence why it's able to break it down, produce the formate, and then this is effluxed out of the cell, removed into the media as well. So the normal function under ambient conditions is that formate is deproportionated to hydrogen CO2 by FHL. If you increase the pressure, the reverse reaction for the reduction of CO2 to formate is highly efficient. The high pressure increases gas solubility, which allows increased substrate availability for FHL. And from this, you get 100% conversion of waste CO2 to formate. And then as soon as it's effluxed from the cell into the media via a pH-dependent efflux channel, this allows you to have a maximal rate of FHL reverse reaction by pH control. So you've got a high concentration outside the cell, a lower concentration in the cell, so the FHL is able to turn over and produce more of the formate. The important take home from this is the fact that you're using intact whole cells. This allows you to use this biocatalyst continuously, and it means that it lowers downstream costs of lysing cells and product extraction from cell lysates, etc. So the longevity of the biocatalyst reduces costs and allows it to be feasible as a long-term solution. So in terms of strain engineering, we want to inactivate unwanted formate utilizing pathways via genome modifications, and this optimizes CO2 reduction to formate and then allows the formate to accumulate rather than be used for other cellular processes. We would maximize FHL expression, as currently it's not. It needs to be 75 times more efficient for it to be commercially viable. So we need to improve that overall productivity, and perhaps looking at engineering heterologous enzymes to remove gaseous impurities found within the waste gases that we'll be using. This allows implementation of this system in a wider range of settings and not just biogenic CO2 systems. So in summary, the conversion of waste gases to commodity chemicals such as formate is a natural property of the host and requires minimal modification. This process can be used as carbon capture CO2 recycling technology because we're using a biological system that's native to the host, and it's been shown to be effective and efficient as a whole cell biocatalyst. Because it's whole cell and doesn't require lysing and further extractions, it's suitable for mobilization, which increases biocatalyst longevity and in turn reduces cost. And because it's efficiently effluxed out of the cell, you've got no need for costly DSP to recover the product. and forming itself is a commodity chemical that can be used as it is or a feedstock for downstream processes for the synthesis of other high-value chemicals as well. The cons of this currently is that as the process stands now, you need a cleaner waste stream as it's more suitable for the reactivity of this enzyme. For example, biogenic CO2 from ethanol production is most suitable. But again, this system can then be engineered further to overcome this con of the system currently. And that's everything from me. Thank you for your time and the opportunity to present, and I'll answer any questions that you have.
Thank you very much, Roxanne. And yeah, we put any questions you have, please, in the Q&A box, and we'll come back to that later. So thank you again. We'll move on now to David Ortega, who's the founder of Phase Biolabs. Now, David's in the US at the moment, and he's joining us, but he's provided us with a video to watch through now. So we'll put that on the screen and listen to that. But David,
good morning.
This for Q&A.
My name is David Ortega. I'm the founder at Phase Biolabs. I want to tell you a little bit about our company and how we're enabling decarbonization via CO2 upcycling. Our motto is, don't just capture carbon, turn it into something valuable. We're on a mission to make things, like chemicals and electrofuels, from CO2. And our vision is a world without oil. We're accelerating decarbonization by enabling emitters to generate new revenue from their waste gases. We don't see gases as waste. We see them as the feedstock for the future. Before telling you a little bit more about Phase Biolabs, I want to give some background and some context to give perspective on how we approach this problem. In the UK, we already recycle a large proportion of the waste that we generate. Unfortunately, this doesn't apply to emissions. On the flip side, this represents a massive opportunity to valorize this huge feedstock into value-added products like chemicals. It's worth describing the nuances and differences between a few different acronyms that are used in the industry. Carbon capture and storage refers to storing of the CO2 of carbon as the CO2 molecule. An example of this is sequestering CO2 in underground caverns. Sequestration in this way happens for the long term, which means that carbon is stored for more than 100 years. Carbon capture, utilization, and storage refers to storing CO2 in or as a product, again for the long term. An example of this is concrete, where CO2 is injected into concrete during the curing process, sequestering it for the long term. Carbon capture and utilization refers to the conversion, recycling, or upcycling of CO2 in a product. An example of this are chemicals. In this case, carbon is not stored for the long term. Although CO2 is not the most potent greenhouse gas, it is the most abundant. We generate more than 10 times more CO2 than carbon monoxide and methane put together. So when we're looking to develop solutions to this problem, we should really be focused on developing technologies that can use CO2 as an input. Not all gases are the same. Carbon derived from biomass is renewable, or referred to as biogenic. When CO2 from biomass is released into the atmosphere, it doesn't result in a net increase in the carbon in the atmosphere. This is in contrast to fossil-derived carbon, which is non-renewable or non-biogenic, because when it is released into the atmosphere, it does result in a net increase in carbon in the atmosphere. What this means is that products, the sustainability and greenness, if you will, of a product not only depends on the energy being used to manufacture that product, but also on where the carbon came from. Companies are starting to pick up on this. This is an example of the carbon rainbow developed by Unilever, and which describes where carbon is coming from. Not all sources of carbon are the same. So when looking to access, it's worth considering the different point sources that are available. Higher quality CO2, meaning CO2 that is present at a concentration of greater than 90%, is available from sources like industrial brewers and ammonia plants. There is a large quantity of lower quality CO2, which is found in concentrations between 10 and 60% of a flue gas composition. You can find this CO2 in cement works, steel mills, and petrochemicals or refineries. In the future, we envision that direct air capture will be a substantial source of renewable and high-quality CO2. There's a lot of interest in developing technologies to recycle CO2 or upcycle CO2 into renewable chemicals and/or fuels. But not all technologies are the same, even though the end product might be the same. This graphic developed by Extantia demonstrates or illustrates the various different types of technologies being used. On the left, we have thermochemical technology. In the middle, we have electrochemical. And on the right, we have biological. As you can see, there's a lot of companies, startups primarily, developing these technologies. But unfortunately, most of them are still in lab and pilot scale. There's only a handful that are currently operating commercially. According to McKinsey, sustainable chemicals will be worth more than £3 trillion per year by 2050. Currently, 90% of chemicals are made from petroleum, and it's expected by 2050, 50% of all chemicals will be produced using a biological route. We think biology has an excellent potential for enabling this future by converting waste gases such as CO2 as the feedstock for the future, allowing us to produce not just chemicals, but other products such as plastics, rubbers, and textiles, all of which require chemicals for their manufacture. Phase Biolabs wants to make renewable chemicals, starting with ethanol. Ethanol is a useful industrial chemical, currently used for the cosmetics industry, as a disinfectant, in pharmacare, and in print packaging. Synthetic ethanol is currently used to supply these application industries and is made from ethylene. What makes ethanol so exciting is that there are massive secondary markets. Ethanol can be converted into sustainable aviation fuel, but it can also be converted into ethylene. Both of these are large and hard to decarbonize markets. We're developing technology called gas fermentation. This technology is very similar to the existing brewing process used to make beer and wine. We start by sourcing our gases, CO2 from industry and renewable hydrogen produced using renewable electricity. These gases are mixed together. We then bubble these gases into a bioreactor or fermenter. In the fermenter, our proprietary microbes grow off of the gases, eating them and converting them into products, in this case, ethanol. In a final step, we then extract and purify the product. We're currently at lab scale and are producing grams of product per day, but we have plans in action to move towards a pilot, which we hope to commission in 2024. Beyond that, We expect to move into a demonstration facility sometime in 2026, and hopefully, if all things go well, we will be operating commercially in 2028. I think it's important to highlight what hydrogen does and means for chemicals. Hydrogen is currently being supported for multiple different use cases, not all of which are the best use of hydrogen or make the most sense either from a practical or economic perspective. However, using hydrogen as a chemical feedstock and for the production of syn fuels for specific applications does make a lot of sense. This clean hydrogen ladder developed by Liebrich Associates illustrates this quite nicely. Thank you for your time. Join us in delivering a low carbon future. Happy to take your questions. Thank you.
Well, thank you, David, for supplying us with that video. As I say, put your questions in the Q&A box, and we'll raise our questions in the session that we've got left. If we can quickly move over onto Catherine, who will take us through some funding collaboration opportunities.
Thank you, Michael. Good morning, everybody. Hope you've all enjoyed the event so far. I have some great presentations. My name is Catherine Julian Mort, and I'm the Knowledge Transfer Manager for Industrial Biotechnology at Innovate UK KTN. For those of you that are following the BCB project, you will have seen me presenting here a few times. And the main flavour of what I've presented previously was the need for funding for our community. So I am absolutely super excited. I've got some funding for you. I'm very excited to talk you through some current funding and networking opportunities, which I hope you'll all be as excited as me when you get to hear them. So without further ado. So in terms of the key message today, it is all around relevant funding calls and associated networking activities which are relevant for the BCB audience. You've heard some great projects today. So now, if you've been excited by that, now's the chance that potentially you could build your own collaborative projects. So this is all around an incentive coming from Innovate UK around reimagining materials and manufacturing. And there are two key programs that I'm going to be talking to you about. One is sustainable bio-based materials and manufacturing, more relevant for us, but also a parallel competition around resource efficiency for materials and manufacturing, which is abbreviated to REFORM. So there are two CR&D study competitions that are coming live very soon. So please get your pen and paper ready and make some notes of these, because you won't get these slides in time, I don't think, especially for the SUSBio competition. So get your notepads ready. So these two competitions have up to £12 million total funding, which is the most money that we've seen for a really long time. So core areas are encouraged. So focused on future economy of materials, smart design, resilient supply chains, world-class production, and longer in use and reuse. So we're not focusing on enabling areas. These two CR&D study competitions are all around joining the dots, and collaboration is absolutely and fundamentally encouraged. So I'm going to just give you a little bit more information. So this is what you need to be aware of, is that for the sustainable bio-based materials and manufacture, it is a mouthful, so I'll call it SUSBio from now on. The CR&D competition opens next Tuesday. So 7th of March, it opens and it closes 8 weeks later, the 3rd of May. So it's not much time to build your consortia, write the project bid and submit and win all the money for your project. So please do check this out this afternoon if you are interested. So this is a little bit more information on it. So it's for UK registered organisations, and they can apply for a share of up to £12 million for collaborative research and development. So the project pots are going to be between 300,000 and £1 million. So, you know, this is a big deal. We've been waiting for something like this for a really long time. And this competition is all around developing step change improvements to sustainable biomanufacturing in the UK. So these are the themes that your project must focus on to be eligible. I'm not going to go into scope in any great detail. These are just the key themes. The scope and more detail will be given next week. So this is just to whet your appetite. And if this does align with you, then obviously you need to find out a little bit more about it, because time is of the essence. So in terms of the key themes, so it needs to be around improving extraction of existing bio-based feedstocks and optimizing these processes. So if you've been on this BCB journey, we have done quite a lot of webinars around the industrial applications of biomass, and there was a report that I'd written around biomass to chemicals with recommendations. So hopefully there will be some people online today that this will be relevant to. So using biotechnology-based systems for developing alternatives to traditional manufacturing processes, including processing and catalysis for sustainability. We talked about this a lot here today. The design and development of future advanced bioproducts with improved or differentiated properties. And the final three key themes: the discovery of novel or optimization of enzymes to whole organisms for biomanufacturing. Securing value from non-food crop biomass and other waste streams. Again, super relevant for us. And finally, improving manufacturability and consistency at scale and progressing the development and adoption of biotechnology across multiple manufacturing industries and sectors. There's a lot of information there. If you go to Innovate UK KTN's webpage, we do have an actual web link to this that you can go and read further details. So please do go and check that out. So the competition launch again, 7th of March. I just want to reiterate this, 7th of March. We have our webinar. It's between 10 and 1. I've put the event link here. You might be able to, I don't know whether Dana or Michael will be able to post that into the chat box for you whilst I'm speaking. If not, I can do it after this just so that you've got it. Please do register for this event today if you are interested and you haven't done so already. There's going to be scope definition presentations given by Innovate UK, so you can ask all your scope questions there. There is also going to be a networking opportunity after the main presentations. And this is where we have a call to action today for you guys. So if you want to be a part of a project, we are going to have a digital networking brochure for everybody that's interested. We've already got 60 people that have already filled out these slides, but you have got to be in it to win it, guys. So if you haven't done it, please register and submit your networking slide today, because the closing date, I think, is first thing in the morning. So I'm glad I've got the opportunity to speak to you in this event today. So hopefully anyone that's missed this call will see it. So this is your call to action. Once you register for the event, there will be a slide for you to fill in. And it's just a good way of capturing all your information, a summary. So this is not going to take you longer than 10 minutes. So who you are, where you sit in the supply chain, what's your project idea? Do you require a partner? I'm assuming you will if you're filling this out. If yes, what type? So this is for the benefit of other people that are going to be going through the brochure looking for project partners. And then you can have the opportunity to network with them live Tuesday afternoon, or if you need, other formal introductions, then we can facilitate that. So this is your chance. So please do this afternoon if you can. So the next competition is Reform, so resource efficiency for materials and manufacturing. This opens a little bit later. This again is CR&D competition, £12 million total funding, so exactly the same amount of money. This opens on the 31st of March, so a little bit later on, open for 8 weeks, closes on the 26th of May. So we do have another competition brief webinar from Innovate UK KTN, which is organised by my colleague AJ. This is the 21st of March. If you want to know more about the scope, please do come along to this. Event link is below on the slides. You'll find it on the KTN site as well. And finally, we have an actual, real, live, face-to-face event in London in the beautiful QE2 building in Westminster, 4th of April. So we've tried to avoid the train strikes. It is, before the Easter break, so hopefully people can make it. And this is all around reimagining materials and manufacturing as a whole. So you're going to be hearing from Innovate UK around what their vision is up until 2050. They're going to be talking around SUSBio and Reform in a lot of detail. Of course, we will have had the scope and events prior to that, but if you've got more questions for them and you want to know what else is going on from Innovate UK, it's a really good opportunity. They're going to be talking around ED&I and how that's really important for your applications, what it means and how to make sure that you encompass that into your applications. There's also going to be networking in the afternoon, predominantly for Reform as SUSBio. At this point, I would have hoped you would have found your project partners because it is a few weeks in or a month in. But there will be drop-in stands if you're in and around London. Innovate UK will be there. We will be there from Innovate UK KTN. Catapults will be there. RTOs will be there. There'll be people there helping you understand what these competitions are and just really there to answer any questions. So please do sign up for that as well. So lots of things going on. 3 events, 2 webinars, 1 face-to-face, all around this higher reimagining materials and manufacturing incentive with the 2 competitions, CR&D. So in terms of how we can support you at Innovate UK KTN, so we can help innovators find new partners for their project proposals, and we can also facilitate introductions to any key stakeholders across several sectors, including Chem and IB, materials and manufacturing. So we've got a really large database of contacts that we can link you up with. We can also review draft proposals if you get them into us in good enough time, if you are new to Innovate UK funding, and we can provide you with some guidance. Just to touch on other relevant funding calls, which you may be interested in on this audience, there is an Eng Bio funding call, which I've put the link to there. My colleague Dana will know more about that. We also have the wonderful iBioIC conference, which I'm pretty sure all of you have attended previously. It's one of the best conferences in the UK for biotech, bioprocessing. That's the 15th and 16th of March. So there's a link I provided there. Please come and join us. And also there is Scottish Enterprise CO2 Utilisation Challenge, very relevant for today's speakers and subject area. It's already open. It closes the 31st of March, 2024, so you've got lots of time, but just to stipulate that this grant is only available to companies based in Scotland or those with the goal of establishing a presence within Scotland to carry out R&D and create jobs. We do have a comprehensive funding slide, which we will send out to everyone as well, along with my slides, but these are the key ones that are probably most relevant to this audience. So if you are unsure which funding opportunity is best suited for you, there are some nuances within the scope. We do warmly recommend that you join these events. These events are for you. please come and join us, and our team will be able to support and advise you further. So I have got a list of people who you can contact within the various subject areas within Innovate UK KTN around biomanufacturing, chemistry, industrial technologies and manufacturing, and materials. There's quite a few different people you can contact. And please sign up for the newsletters for materials, manufacturing, and Chem and IB within Innovate UK KTN to get all the latest news. So that's all from me. It's a whistle-stop tour of what's available right now, but I hope you will be in agreement with me that these are exciting times for our communities, and just get involved. Just come to the event, see what's available, and hopefully you guys will build some wonderful projects, and we'll hear from you in the future about how you've been doing.
Thank you very much, Catherine. Some really exciting opportunities that we have. So yeah, please let us help you, and let's take advantage of that opportunities that exist. I think what we now do, we are running a bit behind, but we'd like to go into our Q&A session. And if I could ask Dana, are there any questions that you can see that have been asked that we want to put to the panel?
Yeah. Unfortunately, Roxanne had to leave, but Ruben offered, he's also from Ingenza, to step in. So Michael, would be great if you could add Ruben to the panelists, because there's a question for him around the stability of the biocatalyst. But while we sort it out, there's a question around the requirement for electricity and hydrogen, and how renewable energies can be used, and how this aligns with, you know, being net zero, and the net zero, the carbon capture and stuff like that. So any views on how to scale up renewable energies in the UK, and how to align that with our goals to capture carbon dioxide? I don't know if anyone wants to take that question. It's a big question, I understand.
Well, all I'll say is it's definitely needed, but I don't know how it's going to be done. But it's, you know, we've got to, I'm sure there'll be funding out there to do that. And yeah, and there'll be people working on it. I don't know if anybody's got a more concrete answer than that.
No, I'd say from the community work that we did with the action plan, it's been identified as something we need to find that answer out. And as we go through electrification and we do fuel switching, that demand for other resources going up. So I think part of it is understanding what is our need now and what will it be in the future. And I think there's a lot of the experts we've talked to, I think nobody's 100% clear of the answer. We know it's needed, and so it is a problem we've got to address. And I think we need to work as a community to help put a number to that as well, what we need.
Thank you.
Michael, if I was just add briefly to the question, thank you to the person who raised the question in the first place. I think when it comes to hydrogen source, there are quite a number of ways producing hydrogen, some of them more renewable than the others. I concur what Michael just mentioned. It's very difficult at the moment to predict which technology is going to win. But I could say that this space is evolving very rapidly. And I still think that the renewable energy is the way going forward. But how that renewable energy is going to be captured and utilized, distributed to meet the demand from all the industry which has urgent need for decarbonization, is that remain to be seen.
Yeah, I could add a comment if I may, just on the hydrogen pricing future. This is what's key for the whole thing. There's forecasts putting green hydrogen right down to less than $2 a kilo. And I think if that comes, it's going to undercut grey and blue hydrogen industrial production. But I think it's very much geopolitical, so it'll be different regions of the world will have that available. So I think the US will lead that. UK is probably advantaged in blue hydrogen as we stand today, in terms of the opportunity for the UK manufacturing industries. But ultimately, I'd hope the UK also has a situation where green hydrogen will compete and ultimately undercut fossil-derived hydrogen, be that grey or blue. So I think it's one to watch, and I think others outside of, certainly we're in the biotech space, will address and resolve that issue for us. Our focus is very much of how do we utilize that hydrogen.
Thank you. There was a general question about the stability of the biocatalyst. Who maybe, I don't know if you want
For my hydrogen lyase biocatalyst.
It says general biocatalyst, so I wasn't sure if it's addressed at you or if it is addressed to CPI. So maybe if both of you can answer the question.
Do you want to go first?
Yeah, sure. I actually put some text in the chat box already. So I mentioned specifically for the Flow2Chem project, what the type of the biocatalyst that we're working on. That's a great question. Yes, so we need to think about the how we're going to renew the biocatalyst to prolong the application, to convert more feedstock into the product and reducing the total units, reduce the cost of a unit of product to produce in that way. So for in our applications, the product itself is within the cells. So at the end of the run, we do have to extract the product out of the cells and make it economically feasible for the scale and application we want to do. So when it comes to the biocatalyst, the one more thing that I think is worth mentioning here is that the product maybe only account for 50 or 40% of the total weight. There's still about half of the biomass that can be used for other purpose. So to me, ultimately, there has to be a biorefinery holistic approach where we just not use the product coming out of the pipeline, but also any byproduct that need to be taken into account. And if there's any opportunities for even upcycling of the byproducts, that need to be considered as well. And on the Flow2Chem project, we do have a partner who specialized in the TEA and LC analysis. So we rely on them to provide us the credible model, which allow us to assess the overall economic and economic feasibility and the environment impact. So we're looking at this, although it's early stage, but we're looking at it from the start, and hopefully, we're going to find out a credible pathway, which is not just help to decarbonize the chemical industry, but also is economic viable to be scaled up further. That's my feedback. Ruben, if you feel like to continue.
Yeah, I'll perhaps just think of the context for what Roxanne described with our specific formate hydrogen lyase process. Ours, to be clear, is not a fermentation process. It's a biocatalytic only transformation. So one of the advantages that offers is we are product manufacturer, in this case, formate, it could be ethanol in other cases, is not coupled to biomass propagation. So if you're running a fermentation, if you're making any other chemical, you're always going to generate biomass with that in a coupled fashion. In our case, we've decoupled that. So in terms of scaling function, turnover function, we have capability to drive much higher volumetric productivities than you can achieve via fermentation transformation of CO2 using a biological system. And because of principles of direct evolution, we can improve the enzyme features of catalytic performance, so improve turnover number, KCAT, KM function, remove contaminants that might be toxifying and inactivating the catalyst. So those are all features that our system possesses. And because it's a fixed bed system, it provides some of the principles we have in chemical manufacturing around improving the volumetric space-time yield, which is obviously and Chang Li mentioned this, is a common weakness with bioprocessing transformations. So I think in our view, we've got a nice marrying of some of the principles of chemical processing intensification we can bring to biotransformation of CO2 to create a value-added chemical product.
Thank you, Ruben. There are lots of interesting questions in the chat box. And we're running out of time, but I have two more. One for David, and it's a general one, David. What are the challenges with hydrogen in terms of sourcing and using in microbial gas fermentation? And how are you addressing them?
Huge challenges. And we're trying to work with local producers of renewable energy. But as someone else pointed out in one of the other questions, there's a lack of energy. You know, we do have an energy problem. We just need more clean energy. So there's no good answer. We just need more access to renewable energy, and that really impacts the sustainability of the end product, of course. So yeah, there's no good answer.
Thank you. I know, Kian, you answered it already in the chat box, but maybe you want to add anything?
There we go. Just unmute myself on this. Thank you for the question. I tapped a few lines in the chat box. Once again, this renewable energy is going to have a huge impact on the process economics. I think many speakers has talked about this already in today's presentations. I maybe just reiterate what I said in the presentation. The future of the industrial power tech depends on the reliable feedstock, and also the decarbonization is a huge impact. It's something that we cannot afford to overlook, especially for the UK chemical processing industry. So it's the one way or another, we're going to have to find credible ways sourcing this renewable energy and hydrogen if it's what is needed to be able to do that. We all know that CO2 is evil molecules that we want to get rid of. Ultimately, it will cost some energy to do that. There's no way to going around of the questions. The sooner we realize, the better for everyone. I think in this particular case, small companies, SME like Ingenta and Base Biolab, and also together with RTO like CPI and also the other academics and the larger corporates, collectively we drive the innovation in this space. And we do have a very challenging, big challenge to solve, and the time is ticking as well. So I'm just hoping that by giving this presentation, there's going to be more people working in this area, and there will be more funding from the government initiative to help to support this in a very collaborative way to solve this problem in the future. So I forgot to mention this in that presentation. Thank you very much to KTM for organizing this, and that's exactly the purpose of why we're having this conversation here and talk about this issue.
Thank you. And I know we're running over, but one last question. This goes to the group because I think we could discuss that forever. Is considering there are competing or multiple competing outcomes for the carbon from carbon capture, where should we focus, or should there be a focus or a priority on specific outcomes where the carbon should go in terms of products? So, for example, should the technology focus on fuels, or should we focus on other chemicals, materials? Any view from the group?
I think talking about hydrogen utilization, there's been suggested to put it into homes for heating and fuel purposes for homes, but that's been widely kind of poo-pooed basically. So I think in terms of value add proposition, hydrogen utilization to make chemicals makes a lot more sense. So from industrial exploitation of renewable hydrogen, I think the chemicals is a really exciting and a prime one for we should be supportive of generally, versus other sectors which may also consider hydrogen utilization opportunities such as transport and heating.
Anyone else would like to add? Sean?
I guess the same will apply to CO2 capture. It's the value added applications that are going to lead the way, and then potentially move on to fuel, perhaps, or I guess the fuel's got the volume, but in this particular case, it's probably harder to do. So yeah, I tend to agree with Ruben.
Okay, good. Then I'm going to hand back to Michael.
Well, thank you very much for all the speakers today for joining us and giving us some real great insight into what's possible and what's in the pipeline. Apologies, we have got some questions here that we haven't had a chance to get to. We'll take a look at those afterwards, and if we can, we'll come back to people. I think what I'd like to do now is to hand over to Kim just to give a bit of a wrap up from the BCB project's perspective.
Sure, I'll just share my screen. So if everybody can see that. Good morning, everyone, or good afternoon, everyone. My name is Kim Cameron. I'm part of the business engagement team at the Industrial Biotechnology Innovation Centre.
Kim, sorry, we can't see your slides. They haven't been shared yet.
Right, hold on, let's try again. How about now?
Perfect.
Better? Okay, thanks. Yeah, so as I said, I'm Kim Cameron. I'm one of the business engagement managers at the Industrial Biotechnology Innovation Centre. I thought it'd be helpful just at this point in the project to give a review of our achievements to date as the ERDF funded phase of the Bioeconomy Cluster Builder comes to an end. So as you may have noticed, events are a large part of what we do. We've delivered, including today's event, 30 events over the course of the project. And these are all about raising awareness of what could be done with biotechnology and also forging connections between different stakeholders to support innovation. They have a mix of online and in-person events, frequently delivered in conjunction with a range of great partners. And so we've had around 2,250 attendees across all these events, a mixture of industry, academia, government, funding bodies, and of course members of the public as well. And we've covered a range of different areas, so looking at applications of biotechnology in textiles, construction, agri-food. As Catherine mentioned earlier, we've looked at all the different feedstocks that can be converted into useful products and services. And we've also looked at areas of support that are of interest to early stage companies. So things like life cycle assessment, investment, and digital marketing. And recordings of a lot of these events are available on the Bioeconomy Cluster Builder website. I'll put the address up on the screen in a moment. In addition to events, we have carried out a range of further engagements in a range of contexts. So we've run roundtable sessions and focus groups to help companies overcome challenges in particular areas. And so these have been either experts from within iBioIC and Innovate UK KTN, or wider groups of stakeholders, external partners from academia, businesses, and so on, as I say, to help companies overcome particular challenges. We also produced reports from the Bioresource Mapping Tool. This is a tool that was developed by iBioIC, Zero Waste Scotland and Scottish Enterprise, and it contains historical data about locations, quantities and composition of key bio-based feedstocks across Scotland. So we produced reports for a number of organisations to help them with key business decisions around things like where to locate their facilities and so on. And similarly, we've used the networks of the partner organisations to help companies overcome supply chain challenges. The BCB team have attended a number of third-party conferences, things like Chem UK, Let's Recycle Live, and earlier this year, the SAOS conference. And finally, this is a really significant part of what we do. It's about making ad hoc connections. So introductions, business to academia, business to business, trade organisations, funders, you name it. We're here to make those connections, and we've made hundreds of those over the last 3 years. So looking to the future, as I said, the ERDF funded portion of the project comes to an end at the end of March. But I'm pleased to say that BCB activity will continue beyond that point, and the collaboration between iBioIC and Innovate UK will form the core of that, and our website, Twitter and LinkedIn presence will be retained. Key contacts will be myself at iBioIC and Dana Helt at Innovate UK KTN. So please do keep an eye out for future events. There'll be a programme of events going forward. Get in touch if you'd like support from the project, and indeed send people our way. If there's anyone you think that we could support, then please put them in touch with us. And we're also interested in partnering with organisations to deliver events and activities. So again, any introductions there, please get in touch and we can forge those. And we're also looking for companies to engage with that we can support, and external events to target. So all suggestions are welcome. You can find our contact details on the website. And just a couple of plugs before we go. Catherine's already mentioned the iBioIC conference, which is now less than 2 weeks away. You can find details on the programme. The theme of this year's conference is resilience and the bioeconomy. Got some great speakers lined up. As I say, you can use this QR code or a dedicated website address to find out more. And alongside that, the Bioeconomy Cluster Builder is running a fringe event on Tuesday, the 14th of March from 8 in the morning until 7 in the evening at Glasgow Queen Street Station, one of the main stations in Glasgow city centre. And this will be a public engagement event entitled Made with Biology, which will be a showcase of bio-based products. So myself and Dan will be on hand there along with some colleagues with some great examples of bio-based products. So all that remains now is for me to thank all of you for supporting the Bioeconomy Cluster Builder. It's been great to have so many of you at our events over the last 3 years. Thanks to Dana, Raj and Catherine at Innovate UK KTN for their support of the project, and to Lindsay, Andrew and Russell at iBioIC for making the BCB such a success. And thanks also to everyone behind the scenes at iBioIC, Innovate UK KTN and Scottish Enterprise for helping us keep the show on the road. So that's the Oscars speech over with now. I'll hand back to Michael. Thank you.
All right. Thanks, Kim. And I think just to follow up on that, it's just a reminder of where we are from the Circular Economy Innovation Network and the action plan. We're still working on delivering on the actions within that plan. We want to continue growing the community and working with you to achieve our goals on that. And so if there's anything in the action plan, if there's things that has resonated with you, then please reach out. Talk to us. We'll want to work with you and help take that forward. If there's, again, introductions or collaborations you want, please again, use the opportunity to come and reach out to us. And if there's an opportunity that we can leverage our pilot program on collaboration exchange to actually really help forge some really good sort of across supply chain, cross-sector, multi-partner projects, through that program, then please reach out and have a conversation about that. Just a final reminder, you would have seen it through the chat a lot. We do have the Meeting Mojo, which is a virtual event platform that's going to be open this afternoon. The actual event platform itself is open this afternoon for scheduling one-to-one meetings. They're short introductory meetings between delegates that have signed up. But actually, the beauty of this is that actually you're able to direct message other delegates for the next few weeks. It will remain open for just doing that direct messaging. So it's a way of continuing to build some introductions and community. And please, obviously, you've heard about some great funding that's coming. If there's ways that any of the people that have spoken today can help out from Innovate UK, KTN, from iBioIC, please take the opportunity to reach out and take advantage of the help that's on offer. And that is really, thank you for all your time, your input and support. Those people have helped pull that action plan together with us, and I know you're going to continue helping support it. And thank you. And yeah, I hope you all have a good day, and may speak to some of you this afternoon. So I think we've got a change to do. I think it's now we need to get on and do it. Thank you very much.